very much, and it's a pleasure to be here. And really making all of the data is following on from Professor Lamb's theme about being rather poor. So if you're rather poor, you need to make the most of what you've got. So that's what I'm really going to be talking about. So really it's considering these cohorts in China. What special opportunities do they present for us that we can use to do something we couldn't otherwise do? And I think the most important thing we've got is the anomalies in disease patterns we can use to get insights we wouldn't be able to get from studies in the West. So using the differences here, and maybe specific genetic differences may generate insights. And my favourite one is learning from failure. I think that being wrong is one of the most instructive things possible, because then you have to rethink and come to a new conclusion. So to clarify just what these anomalies look like, we have, I've got a graph here of the trends in ischemic heart disease from 1950 to 2010. And they vary wildly between places. So that in North America they went down first in men, in Northern Europe a bit later, doing something weird in the former Soviet Union, and then China completely different. And then in women also, sort of very varying patterns. So, but the difference is that historically we have these lower rates of heart disease in China. And then throughout Asia, the higher rates of diabetes, even though people are not particularly fat. So here's the US with 8% rate of diabetes, but most people are overweight or obese. And then India with a much higher rate of diabetes, but fewer people who are overweight and obese. So we seem to have diabetes without necessarily the obesity, and the diabetes people have has different results here. So in the West, diabetes is often followed by cardiovascular disease, but in Asia it's more followed by kidney disease for reasons we don't fully understand, which means either it's got different causes or it's a different disease. And all these are questions which would be helpful to answer so we can deal with these epidemics better. And equally, we have a lower rates of autoimmune diseases, again for reasons we don't understand. Is it connected with any of these other diseases? We don't know. But it must be telling us something. So my question is, what is it telling us? And what can we do with it? And we even have a problem with actually predicting disease. Because you need to predict disease, particularly for cardiovascular disease, to treat people. So you want to identify who's at risk and then treat them. And you want to identify them very cheaply, because you want to be able to screen everybody. So that most places in the West, people are assessed based on smoking, diabetes, blood pressure and lipids, which are quick and easy to measure, and then they can be assigned a risk and treated preventively if their risk is high. And what we see here is 10 years ago, when people were predicting ischemic heart disease in China, they found that at every level of risk, the Americans, the US men, were at higher risk for every group than the Chinese men. So at that point, you were predicting that Chinese at the same level of risk factors had a much lower level of ischemic heart disease risk. But now we've got a new global model called global risk that came out recently, which says slightly differently that the proportion of people at risk in each group tends to be, when it's in low risk groups, it's mainly US people, and in high risk groups, it's mainly Chinese people. So now the prediction models are saying that people in China are at a very high risk of cardiovascular disease based on the same risk factors. So we seem to have some sort of discrepancy here, and part of the discrepancy, I think, is because the global risk model hasn't ever been validated. It's only, and it's calibrated to predicted risk, which may give a weird answer. But it shows us the issues in that we find it very difficult even to predict coherently who might be at risk of disease. But I think even more so, if we want to intervene, we have to move beyond predictive modelling, because predicting is just projection. It doesn't tell us how to intervene. What predicts ill health may not necessarily also cause it. You know, if my grey hair predicts, you know, that I'm older and that I will die sooner, but it's not my grey hair that causes it, and dyeing my hair black will make no difference. So, you know, prediction is different. So prediction is great if you want to project patterns of disease, if you want to identify vulnerable groups like risk stratification, or project trends, or even catalogue risk factors, it's fine. And, you know, here's a nice example of a prediction model where you can predict flu trends. But what we're after is explanatory models, models that explain the past and enable you to predict the future with some sort of model that makes falsifiable predictions. And so here's an example of those sorts of scientific models that we all know of. They have a sort of underlying structure, and they provide general explanations, not a catalogue, but a general explanation. So if we want to know how to intervene, we need these general explanations. And the question is, how do we obtain them? And that is not an easy problem at all. And if we look at cardiovascular disease, we can see that so far, we can see how we're doing, so that now in the top 20 causes of disease, the top one is ischemic heart disease globally for years of life lost, and then stroke is the third one. So cardiovascular disease is incredibly important. And this is what Michael Marmot said in 1975. He said that conventional risk factors only partly explain the observed gradient in coronary heart disease. So he was saying we can't explain the patterns. And here we have Esati writing about the same thing in 2015, 40 years later. He's saying the same thing. Measured risk factors and treatment variables, while important, explain neither why the decline in cardiovascular disease began when it did, nor many of the similarities and differences between countries or between men and women. So 40 years on, we really haven't made any progress at all. And Esati's solution to this problem was to say, well, cardiovascular disease is going down fast, so let's do something else. This one's too hard. That doesn't seem to me to be a good solution for two reasons. Firstly, as you mentioned, there's this vast difference between men and women, in that men are much more vulnerable to cardiovascular disease than women. That's why they have a substantially shorter life expectancy than women by about 4 years. So we just ignore that and say, well, that's just the way it is, or we try and do something. And also, the cardiovascular disease may be declining sharply in Western countries, but it is not declining sharply in developing countries. So to say, well, there's no problem in Western countries, so we'll forget about it, again, doesn't seem to me to be a good solution. So we go back to these anomalies. When quite soon after I started here, Professor Lamb asked me a question which I didn't know the answer, and it wasn't even a question about smoking. He was asking me a highly motivating question: why hasn't Hong Kong had an epidemic of heart disease? Because normally economic development, then you get an epidemic of heart disease. Why hasn't Hong Kong had one? That seemed to be, a very interesting question and relevant to whether one would occur in China later or not. And so if you look at these age standardized rates, you can see that no, there hasn't been an epidemic. They're going down, if anything. So, 1976 to 2006, they've gone down. There's overall men, of course, higher than women, and then women less. The rates are going down, but normally they go up. What went wrong? So one thing we did was we tried to break these trends down by age and period and cohort. And then we saw something very interesting in that this is the period effect, which is not terribly great, suggesting it's not things in current life that make a big difference. But we saw instead that for men, we get this upturn in about 1945 to 50. So what we're seeing is that something about being born into a more developed environment appears to be associated with a higher risk of heart disease for men, but not women. Now that's very interesting, because we know there's higher rates of heart disease in men. We know they emerge with economic development. So it's telling us they emerge as something about growing up, because they have a cohort effect. So it's a generation born into better living conditions where it's a problem. So that was then interesting and informative. So I went on from that to make a descriptive model of what happens to patterns of disease with economic development. Because, first you can describe and then you can explain. And it seems that, as Maggie said, with economic development, it takes you these 6 generations to reach your full height. But very quickly, you reach sexual maturity earlier. So in Hong Kong, we have age of menarche as 11, but people in Hong Kong are not as tall as Westerners, and they're not as heavily built. Which you can see all these things by just the comparisons in the audience. These ones are visually obvious. And then we seem to get epidemics which vary with the number of generations. So at the beginning of economic development, you get diabetes epidemics. And that sort of seems to be the case almost everywhere. Poorer people or migrants from poor countries to rich countries always seem to have higher rates of diabetes than the populations they join. And of course, we don't know what the rates of diabetes were in Europe 200 years ago, because they weren't recorded. They seem to have more obesity in women at the beginning, and then obesity in men. And this epidemic seems to come later, not immediately. But we wouldn't realise that in the West, because economic development in the West started 200 years ago for many countries, and the epidemic in heart disease actually occurred sort of in the early 1920s in the US, so it was not immediate. So it seems as if these things take time, but why? And so after that, if you've made a descriptive model, which might be good for prediction, then you have to make a explanatory model. So after that, I think how to explain this. And one approach to explanation normally used in science is to build on the work of others. So here is a picture of the coin, the £2 coins from the UK, which say standing on the shoulders of giants, from Newton. Because Newton said, if I have seen further than others, it's only because I was standing on others' shoulders. And in the UK, we're so happy with Newton that we put it on the coins. And I carry the coins with me to remind me of that. So whose shoulders are we going to choose? So I decided to have a look at evolutionary biology, which immediately tells us something interesting. It's saying that fitness is not the same as longevity. It is not our role in life to live forever. Fitness is reproductive success. That's what we're aiming at here. And so animals, at least, and we are in some sense one of them, we have environmentally driven strategies to maximize production, which might involve trading off growth against reproduction and longevity. And then I found this wonderful experiment in mice. So they gave mice different diets. So here's some environmentally driven stuff to see what would happen in terms of longevity and in terms of reproductive success. So they found a diet where the mice lived a long time, and so that was the diet that had very little protein and a lot of carbohydrate. So you need the protein carbohydrate that mattered for that diet for long lifespan. And then they found a diet which was better for fertility, lots more protein. So it seems, exactly an example of that trade-off. Environmentally driven, you can either live forever or you can go for big gonads. if circumstances allow. And as the question to which I'm sure you all know the answer is, what sort of diet do you think the mice prefer? Yes? Do the mice want the big gonads or to live forever? Mice left to themselves prefer a high fertility diet. And would you suspect that humans might, in a more plentiful environment, think they needed to do the same thing? Because then you can begin to answer the question of how economic development will affect health. In that, and so I made up this complex model, which I have to apologise for, to say that if we get better living conditions, we will then be able to grow faster and to grow bigger, and we will do it by upregulating the things that drive growth, which in infancy we don't really know. Childhood is growth hormone, and then of course sex steroids, because we want to be reproducing. And then, in order to understand how economic development affects health, you then think, how does sex steroids affect health? And we already know about estrogen because we tried that one. And so, but testosterone we don't really know about. But based on what we do know so far, what we said back in 2005 actually, but only published in 2008, is that testosterone causes cardiovascular disease. And since then, Health Canada has said so, and the FDA has said so, and in the US the sales of testosterone have fallen. So then you've got drivers of testosterone, new targets of intervention, a whole new way of thinking about what causes disease. And whatever drives testosterone probably causes prostate cancer and some other cancers as well. And we can test these theories using the cohorts that have been created by Professor Lamb's efforts across the life course, because they span the entire life course. And so one thing we've done is you can show that, consistent with the theory, if you grow fast, ready to reproduce earlier, you have poorer cardiovascular disease risk factors. Earlier age of menarche, worse risk factors. And we can show that, this is environmentally modifiable in terms of air pollution. Changes age at puberty with different effects in boys and girls, so it must be acting as some form of endocrine disruptor, which is interesting. So there's modifiable determinants. And finally, the one I spent longest thinking about was, I wanted to find something. If testosterone might be bad for you, then things that reduce testosterone will be good for you. So I tried to find some. And it's very difficult to find since there's no literature, so I just looked at the bodybuilders' websites instead, on the theory that things bodybuilders hated would be the things that would be really good for lowering testosterone. And there I found glutamate, and then when I looked I found that yes, glutamate reduces testosterone in rats, reduces LDL cholesterol, and may reduce blood pressure, and 3 genome-wide association studies have found that a gene associated with glutamate reduces heart disease. And glutamine appeared on on some of the slides from Finland as one of the things. Lower glutamate was good. Sorry, higher glutamate was good. So then I tested this in both the biobank, the Guangzhou biobank, where higher glutamate reduces LDL, associated with lower LDL cholesterol, and in Haynes looking at mortality, lower risk of dying of cardiovascular disease. So that seemed to be a new risk factor found by looking for things that drive testosterone. So my next step is to do a little RCT where I give people glutamate and see what happens to their testosterone. You have some other sort of interesting genetic differences here which have a pattern to them. And the other thing I just wanted to mention was about refutation being so useful, because we talked about cholesterol earlier and how the drugs that change cholesterol don't work, and Eli Lilly just lost a lot of money on one which was cancelled 2 weeks ago. It works in terms of what it does to cholesterol, but it clearly is a correlation, not a causation. So, okay, it's told us it's correlated. What seems to me most interesting is there's no correlation without causation. So what we want to go back and do is say what caused that correlation. It's now giving us new information. Failure gives us new information. So how do we answer that question? And then you have to generate explanatory models. And luckily, we've got all the materials we need because we have a zillion point-to-point relations already there in PubMed, where people have done RCTs or done experiments, so we know a great many relations. And all we have to do is reassemble them into a pattern. So I reassembled these into a new pattern which explains all the relations. And so this is a hypothesis-free way of generating new explanatory models by finding something where you've got refutation and then explaining it using the data we have. Because although I did this by just building the model by hand, you could build a computer program that would select the best model for you, hypothesis-free, generating new explanatory models. So what I really want to say is how our setting is so useful because it creates these new motivating questions, and we have resources. And I think the other thing is if we answer them in the right way, in a scientific manner, trying to find an explanatory model, we may be able to generate new actionable insights to do something about the major causes of disease, like, say, glutamate. And the only other thing is I wanted to acknowledge everybody else who has worked with me on these things, including particularly, of course, Professor Lang, because he's the one who set up almost all these cohorts with Professor Lang, and also asked me that interesting question. I have to add, Professor Long stood at my side and said, do science. You must argue this scientifically, not in some other way. So, thank you very much indeed.